In this section of this lecture, I will just try to explain that how population inversion achieved in semiconductor laser, and as a result we get the laser light. So the first of all, it is necessary to understand the idea of energy band for semiconductor materials, which we are using here to explain the semiconductor laser working. So for the p-type semiconductor materials, we know that this is our valence band, this is our conduction band. In between these two, this is the top of the valence band, this is bottom of the conduction band, and this forbidden gap is known as energy gap of the semiconductor materials, where these line represent to the Fermi energy level in p-type semiconductor, that is very close to the valence band, just above the valence band. Just above the valence band, this is the Fermi energy level. So the point is basically related to the Fermi energy levels, where it lies in p-type semiconductor and n-type semiconductor. This is p-type semiconductor and Fermi energy level lies just above the valence band. In n-type semiconductor, the Fermi energy level lies just below the conduction band. This is bottom of the conduction band and this is the top of the valence band, while this line represents the Fermi energy level. So in general, the Fermi energy level in p-type semiconductor is just above the valence band, and here in n-type semiconductor it is just below the conduction band. So what happens when we join this p and n junction? What happens at the time really with this Fermi energy level, which is above, and this Fermi energy level is below as compared to this one. So when we join p-type and n-type semiconductor materials, electron starts to flow towards the p, and holes, which are majority charge carriers, move towards the n-type, and near to the junction electron hole combinations take place, and as a result, after some times we observe that there is no more flow of the electrons towards the p-type and holes towards the n-type. So there is no flow of charges. That situation is known as equilibrium condition. When equilibrium condition comes, then that time Fermi energy levels towards the in p-type semiconductor and in n-type semiconductor becomes uniform, like this one. So this is our p-type semiconductor. This is top of the valence band. This is valence band. Top of the valence band. This is bottom of the conduction band. This is conduction band. In p-type semiconductor, this one is the conduction band. In n-type semiconductor, and this is the valence band, EV. So top of the valence band and bottom of the conduction band in n-type semiconductor, this is slope, which is known as internal barrier of the p-n junction, and this is the top of the conduction band, and this one is the top of the valence band, and the gap in between the conduction band and valence band is known as energy gap. So what is the idea? Idea is actually we have two containers of different level of water. One is this one and second is this one. Right? So when we join these together, suppose I make a small hole here and a small hole here and join these two with the help of a pipe. What will happen? A water basically from this higher level comes toward this side, and after some times it becomes at the same level. The level is same right now. This is the idea. Similarly, when we join p-type semiconductor and n-type semiconductor both together, this Fermi energy level basically these energy levels just uprise, and these towards the end, these downwards, and situation becomes like this one. And in terms of the energy band diagram, we see this is the Fermi energy level, this line. Here the space above this line represents to the holes. All these states are filled below this Fermi energy level. So these red lines basically indicates to the energy levels. Those energy levels are completely filled. And this is p-type semiconductor, and here this is n-type semiconductor. This is the conduction, bottom of the conduction band, and this Fermi energy level is just above the conduction band. So all the energy states below it are completely filled, and above states are empty. So there are majority charge carrier in conduction band. This is the idea of Fermi energy level. When we use the concept of Fermi energy level in a p-n junction diode. So what is the idea? Idea is when we join p-n junction, the Fermi energy level which was with a gap, it becomes horizontal, it becomes equal, in equilibrium. This condition comes when the flow of electrons without external biasing stops in a p-n junction diode. So this is our p types, this is n type p-n junction, and this form which is shown here is in terms of the energy band diagram. This slope, so the internal barrier, and this width, this distance which starts from here and ends up to this point, this region is known as depletion region. So without any biasing, what we are observing, that there are some holes, there are charge carriers which are electrons in n-type semiconductor, and in valence band there are some holes. So this is the idea, and this is V naught, this is barrier height. So electron cannot jump from n side to the p side. And one more important thing is which I forget to tell, that this is very highly doped semiconductor material. This is P plus and this is N plus. So because of this, majority charge carrier are into valence band, so into the conduction band, and majority holes are into the valence band, right? So because of this highly concentrated of semiconductor materials, then we apply external biasing. When the current is very small, these depletion region basically reduce. Why? Because this height of the potential barrier starts to reduce. So as a result, electron from the conduction band, from p type, jumps into the valence band, and as a result we observe some photons. These spontaneous process basically occurs at a very small current, and this function we observe in LEDs. When we start to increase the current, this barrier height basically becomes almost zero. So you can see here the current approach a threshold value, and then we observe stimulated emission. Here we observe the population inversion. Actually, what is population inversion? In semiconductor case, large number of the electrons are in conduction band and large number of the holes are in valence band. This kind of situation which we are observing here is known as population inversion. And here this is our depletion region. So in this depletion region there are majority charge carried in conduction band and there are vacancies into the valence band of p-type semiconductor. This energy level, this is the bottom of the conduction band of p-type, and here this line indicate to the Fermi energy level towards the n-type. Here this is the Fermi energy level in valence band, and that is very close or almost to the top of the valence band in n-type semiconductor. This point is important. Here Fermi energy levels height is almost to the bottom of the conduction band towards the p. This is p types, p plus, and this is towards the n plus. So Fermi energy level here is almost at the same height as of the top of the valence band, and here this is the top, this is the bottom of the conduction band, and this one, the line represent to the Fermi energy level towards the n. So Fermi energy level is this one is the Fermi energy level in p type. So this gap is basically from this Fermi energy level in valence band, and this is correspond to the Fermi energy level in conduction band, that is EV. Energy gap between the bottom of the conduction band and top of the valence band, that is EG. Now the question is how transition basically take place in semiconductor laser. When the current is at a particular value, that is basically threshold current, then this electron jumps into the valence band, and when electron hole recombination take place, a photon emits, and also the emitted photon strike with this electron, and this electron jumps into the valence band. So like this, these transition take place in semiconductor laser. In general, gallium arsenide emits 9000 angstrom of the wavelength that comes into the infrared region. So we use gallium arsenide phosphorus, that is comes in visible spectrum, and the wavelength is 6500 angstrom. So the basic idea and important thing in semiconductor laser is to understand the concept of energy band diagram. If one can understand the energy band diagram, that can explain or understand the semiconductor laser working. So I am just summarizing about the semiconductor laser, for which the idea of semiconductor is important. We are using energy band diagram concept. So here the energy band for p-type semiconductor, where Fermi energy level is just above the valence band. In n-type semiconductor, the Fermi energy level is just below the conduction band. When we join these p-type and n-type semiconductors, what happens basically? The some energy level just rise up, and from the n-type they come down, and after some times they becomes an equal position. Like as I have given here an example of two containers in which water is filled up to different levels. At this height the water is filled up to this level, and in second the water is up to this level. When I join it with a pipe, the water comes flow through this side, and after some times it becomes at the same position. So this example is used to explain the Fermi energy levels. When we join P and N junction, then that time electron basically starts to flow towards the P and hole towards the N side, and as a result, nearby to the junction, electron-hole recombination take place. After some time, we observe that there is no more flow of the current, no more electron-hole recombinations. So that situation is basically correspond to this concept. Here, Fermi energy level, this is towards the P, just below the valence band, and here Fermi energy level is just above the conduction band. And what was the idea before? This Fermi energy level was just below the conduction band, and here Fermi energy level was just above the valence band. But after joining these P and N junction, it becomes down below the valence band, and it just rises up through here in conduction band. So right now this is the idea without any biasing of energy band diagram in P-N junction diode. Now next, when we apply some current, as a result what will happen? Electron move towards the P side and hole towards the N side, and a small current starts to flow. So here we are using gallium arsenide, so not it behave like a semiconductor in silicon and germanium. So the electron basically jumps into the valence band, and electron hole recombination takes place, and as a result a photon emits into this side, which is a depletion region. Basically the photons comes from the depletion region. And further, when we are increasing the current at a particular current, that is a threshold current, the stimulated emission basically starts to dominate. In general, at a lower current, spontaneous emission take place, and that we see in general light emitting diode. So light emitting diode works at a small current, but when we reach up a threshold value, then we observe stimulated emission dominates over the spontaneous emission, and as a result we get this coherent light. So here what is happening? The Fermi energy levels is just equal to the at the same where is this bottom of the conduction band, and here this is the Fermi energy levels at very high current. This is the Fermi energy level. This is almost equal to the height of the valence band, top of the valence band. So there is no energy gap in between these two. So potential barrier reduced almost equal to zero. So all the electrons basically which injecting towards the P side, and from P side all the holes basically move towards the electrons, and as a result we get this kind of situation, very high light. So this is I just try to show this one as a depletion region, and from here conduction electron jumps into the valence band, and as a result we observe these photons. These photons move in depletion region, and here we have a reflector of this side of this semiconductor. Then they fill the cavity, and after some times emitted photon starts to come out. A gallium arsenide, the wavelength in general is 9000 angstrom, that comes into the infrared region. So in visible spectrum, that is red color light, that is basically gallium arsenide phosphorus of 6500. Semiconductor laser is used in CD audio player, CD-ROM drives, optical reading, and in optical fiber communications. So this is the main application of the semiconductor laser. So this is the basic idea of semiconductor laser. I hope it will help you. Thank you.